Welcome to our channel, and today we are going to help you understand the paper YUAN 2.0, a large language model with localized filtering-based attention. The text introduces YUAN 2.0, a large language model featuring localized filtering-based attention, LFA, which enhances attention mechanisms by incorporating knowledge of local dependencies in natural language processing. YUAN 2.0, with model sizes ranging from 2.1 to 102.6 billion parameters, uses a data filtering and generation method to create high-quality datasets for pre-training and fine-tuning. It also employs a distributed training approach that optimizes parallel processing, reducing bandwidth needs for intranode communication and improving performance in large-scale training environments. The authors claim that YUAN 2.0 performs impressively in code generation, math problem solving, and conversational tasks when compared to existing models. The model weights and source code of YUAN 2.0 are available on GitHub. The introduction stresses the accomplishments of large language models, LLMs, like GPT-3 and ChatGPT in natural language processing tasks, and highlights their applications in various fields. Furthermore, it mentions that models like GPT-4 perform extremely well on exams measuring human-like knowledge and reasoning. It also addresses a limitation of attention mechanisms in standard LLMs, which the proposed LFA aims to overcome by focusing on local word dependencies. Lastly, it discusses the importance of data volume and quality in model training, noting that even smaller models can surpass larger ones like GPT-3 if trained with high-quality data. The text discusses advancements in the field of language models, LMs, and proposes ways to enhance their performance through improved data quality and model architecture. It starts by noting that smaller models have shown proficiency in specific tasks and can sometimes outperform larger models, though they may not have as broad generalization abilities. Notable examples include Wizard Coder, which excels in code generation, and Alpaca 7b, which rivals the performance of GPT 3.5 with less computational cost. Stable LM's smallest model is also recognized for its reliable generation capability with only 3 billion parameters. The authors believe that the quality of training data plays a significant role, and their research focuses on producing high-quality datasets for better pre-training and fine-tuning of LMs. The work introduces three main contributions. 1. A new attention mechanism called Localized Filtering-Based Attention, LFA, which is utilized in their YUAN 2.0 model. This model ranges from 2.1 billion to 102.6 billion parameters and has been made available for both research and commercial purposes. 2. A method for filtering and generating data that leads to a high-quality pre-training and fine-tuning dataset. Some of this data is generated by LMs, which enriches the dataset and enhances its overall quality. A novel parallel computing paradigm that involves non-uniform pipeline parallelism, data parallelism, and optimizer parallelism. This method reduces communication bandwidth needs compared to traditional parallel computing paradigms. Moreover, the text briefly reviews YUAN 1.0, its previous version with 245 billion parameters, which was launched 2 years ago and digested 5 terabytes of various text data. While YUAN 1.0 excelled in Chinese language processing and demonstrated potential in zero-shot and few-shot learning, it faced challenges with tasks requiring logic and reasoning due to a lack of relevant data in its training set. YUAN 2.0 now proposes a novel attention architecture that improves upon previous models by enhancing local connections between adjacent tokens, drawing on techniques like hierarchical one-dimensional convolutions that outperform the exponential moving average, EMA, structures used in another model known as MEGA. 2.2 Dataset Summary. The text describes how web crawling has typically been employed to gather pre-training corpora for large language models, LLMs, but notes the challenges due to noise in web content, which affects data cleaning and dataset quality. Recently, instead of sourcing from the web, high-quality datasets have been produced using powerful LLMs. Examples given include Self-Instruct, which generates an instruction dataset from a pre-existing seed using a pre-trained LLM. Code Alpaca, which creates a code instruction following dataset named Code Alpaca 20K. Wizard LM's proposal of Evil Instruct for complex instruction generation, and Wizard Coder's use of Evil Instruct to enhance code alpaca 20K, creating a larger evolved dataset of around 78K samples. The text goes on to mention YUAN, a 1.3b parameters model trained on synthesized Python textbooks and exercises, achieving a high accuracy on human eval. The trend is to build synthesized high-quality data for fine-tuning, as with Code Llama, which uses Llama 2 as the base model and has shown state-of-the-art performance. However, the authors present a synthesized dataset of high quality that can be used for both pre-training and fine-tuning. For the construction of the instruction dataset for YUAN 2.0, the text explains adopting methods inspired by self-instruct and eval-instruct. The self-instruct process is simplified by eliminating the classification task identification step and focusing the prompt template on code generation. Eval-instruct is modified by limiting evolution to the depth level and not incorporating breadth level evolution. 3. Method summary. In the method section, only part of the text is provided. It introduces localized filtering-based attention, LFA, within the context of the YUAN 2.0 model architecture. Traditional self-attention considers the entire input sequence without presupposing any dependencies between input tokens, while in natural language, these tokens often have stronger local dependencies. LFA appears to take this into account by focusing on local inputs, which could potentially improve the attention mechanism's efficiency and effectiveness. But the details about LFA are incomplete in the provided text. The text describes a research work that introduces localized filtering-based attention, LFA, an attention mechanism designed to place emphasis on local dependencies in contrast to distant ones. The LFA mechanism is incorporated into the computation of self-attention pairwise weights by using two consecutive one-dimensional convolutions. These convolutions utilize a one-sided one-dimensional kernel to avoid future token information from influencing the current token, and they establish a relationship between a given token and the two preceding tokens. A new structure incorporating the LFA into the YUAN 2.0 model includes an RMS norm module before the output embedding, which shares parameters with the input embedding, and uses SWIGLU as the nonlinearity within the feedforward FFW. Layer, an ablation study is conducted on the LFA architecture using an internal code dataset to evaluate the performance impact of different attention structures. The base attention model is similar to LLAME with added variations. An EMA layer, inserted before the creation of query and key arrays in self-attention, improved test loss by 1.6%, but increased runtime by 29%, deemed too costly for large model training. LFA with a one-sided, one-dimensional convolution kernel size of 7 achieved the best accuracy and a 3.3% improvement in test loss with a 15% increase in parameters. An attempt to lower memory usage in LLM training involved using two smaller convolution kernels of size 2, which maintained close accuracy to the kernel size of 7. Adding RMS norm after the two convolutions further improved accuracy, with the final configuration resulting in a 3.5% test loss improvement for the YUAN 2.0 model. Table 1 in the text compares test losses across different attention architectures, indicating parameter count, time per iteration, and test loss values for each model. For instance, models with LFA utilizing a convolution kernel size of 71HH had 185.1 mem parameters, a 621 milliseconds time per iteration, and a test loss of 1.2093, whereas LFA with two kernels of size 21H2, 21H, and RMS norm had 167.4 parameters, a 631 milliseconds time per iteration, and a test loss of 1.2069. The pre-training dataset described in section 3.2 consists of resources in both Chinese and English, including books, codes, and encyclopedias. The dataset is curated from publicly available sources and refined for quality by filtering and deduplication. Specifically, the code dataset in Chinese includes 4 million synthesized instruction samples developed using programming-related words from the Sogo Input Dictionary to generate programming tasks and Python solutions using GPT 3.5. This dataset aims to cover multiple programming concepts and excludes duplicate and codeless samples. Additionally, the dataset includes the StarCoder dataset of code data in various programming languages. Comments have been translated into Chinese using an open-source model. Quality filtered math data from the past 5 years, including web-based formulas converted to LaTeX format, and math instruction data from open-source datasets have also been incorporated after rigorous filtering and standardization with a focus on LaTeX. For Chinese encyclopedic and book content, reliable open-source datasets were used, and the data was processed by removing fiction, converting to plain text, and filtering improper content. The Pile, another dataset for training large language models, is partially included with certain sections from sources such as DM, Arxiv, Wikipedia, and others being incorporated into the training set after removing less relevant articles. The text describes the process of creating a specialized dataset for pre-training and fine-tuning purposes, focusing on language translation and coding tasks. For pre-training, sensitive content such as authors' information, figures, and captions from Arxiv documents, as well as bad words in both English and Chinese, CNN, is removed from the dataset. The pre-training dataset consists of various programming languages and source materials, such as Python, Java, Wikipedia, and books, each constituting different percentages of the dataset, totaling 100%. For the fine-tuning dataset, which is centered on code, math, and chat tasks, the process involves collecting open-source code instruction datasets and translating English code instructions into Chinese using the GPT 3.5 model. The dataset is then cleaned by removing non-Python programming languages and regenerating Python code snippets when necessary. If multiple code snippets are present, only the first snippet is retained, as it is often the most relevant to the instruction. The text discusses the creation and refinement of datasets for machine learning models, specifically focusing on programming, mathematical operations, and professional examination datasets. For the programming dataset, topic words related to programming are extracted from CodeAlpaca 20K and 2000 LeetCode tasks. A new code dataset is created using these words with GPT 3.5. Two methods, self-instruct and evil-instruct, are used to iteratively expand this dataset. Self-instruct increases diversity, while evil-instruct increases complexity. A rigorous format for the codes is enforced, including function names, annotations, and unit tests. A data cleaning strategy is implemented to remove non-functional or underperforming samples, with lower quality samples being regenerated until they meet the standards. For the math dataset, a mathematical instruction dataset is constructed with 247,000 samples focused on simple and complex operations. Multiple datasets are combined to create a new dataset based on the chain of thought T method after translation from English to Chinese and refinement using GPT 3.5 Turbo. The correctness of the synthesized dataset is verified by comparing answers with ground truth. For the professional examination dataset, the YUAN 1.0 dataset with 3.99 million K-12 subject samples is filtered to 2.19 million high-quality samples that follow the CoT paradigm. Real college entrance exam questions are removed to prevent data leakage. Overall, these datasets aim to improve the accuracy and capability of AI models in generating code and solving mathematical and professional examination problems. The text describes a chat fine-tuning dataset, which consists of various categories that contribute to the content as follows. Multi-turn dialogue, 8.42%. Helpfulness data, 6.27%. Practical writings, 7.01%. Chinese classical poetry, 18.14%. Keyword recognition, 5.1%. Summary, 6.9%. Brainstorm, 6.33%. Translation, 6.74%. Sentiment analysis, 4.18%. Mails writing, 5.42%. Retrieval augmented classification, 6.28%. Retrieval augmented generation, 4.97%. OpenQA, 4.76%. Personality, 4.89%. Improper question, 5.38 cents. To build special datasets that improve retrieval augmented generation classification, RAC abilities, high-quality retrieval datasets containing human questions and informative articles are used. A retrieval model retrieves the 5 most relevant articles for each question, and prompt examples are provided in Table 4. The chat instruction dataset is formatted with user prompts and expected answers separated by SEP. Data preparation includes expanding prompts with GPT 3.5 and cleaning out harmful information, inappropriate length answers, and conducting quality reviews. For RAC ability, prompt examples given in Table 4 require careful reading of the article, using information explicitly stated in the article to answer questions, RAB prompt, or simply replying yes or no based on whether the article contains answers to the questions. RAT prompt. The section describes a distributed training method for large models such as GPT-3 or LMA, which commonly uses different types of parallelism: tensor, pipeline, and data parallelism, collectively referred to as Method 1. Tensor parallelism requires multiple collective communications during training, significantly increasing bandwidth requirements and potentially creating a bottleneck. An equation to calculate the time taken for a single iteration of training using 3D parallelism, tensor, pipeline, data is provided. The equation considers various factors like the amount of communication needed, the size of the model's parameters, and the performance of smaller models on GPUs. For an updated version of the method, YUAN 2.0 with LFA, a different equation is given, with the main differences arising from the introduction of LFA, layer-wise feed-forward asynchronous execution. Details of the time required for each part of the original equation, EQ1, are listed in Table 5, comparing predicted and measured times for the earlier version. YUAN 1.0 training on a GPU cluster took an average measured time of 46.2 seconds per time step, close to the predicted 45.192 seconds. It's mentioned that YUAN 2.0 would require a significantly higher bidirectional bandwidth for tensor parallelism, 745 gigas per second, compared to that available for pipeline or data parallelism, 31 gigabits per second. The table shows the running time breakdown for YUAN 1.0 to 245B, with the majority of the time spent on forward and backward compute time. The text presents a distributed training method for training large language models, LLMs, that focuses on reducing the communication bandwidth required for such tasks. It describes several forms of parallelism used in the process. 1. Pipeline parallelism. This method originally involves evenly dividing the transformer layers across computing devices. However, this can create issues with memory consumption, as the first stages of the pipeline need to store temporary variables for backpropagation. An example given is a 24-layer transformer model, where using uniform pipeline parallelism with checkpoint activation causes the first stage to use about 78 gigabytes of memory, close to the GPU memory limit. 2. Non-uniform pipeline parallelism. To reduce memory usage, the authors propose a non-uniform pipeline parallelism approach, distributing transformer layers unevenly among the pipeline stages, e.g. 2, 2, 3, 3, 4, 4, 4, 2 distribution for a 24-layer model. This change reduces the memory requirement for the first stage to 56 gigabytes, a 28.2% decrease from the uniform approach. Blockwise cross-entropy calculation. To further mitigate memory consumption, especially in the last pipeline stage, the authors introduce a method for blockwise cross-entropy computation that reduces peak memory needs while handling large vocabularies. This is done by splitting the matrices into smaller blocks and computing the loss for each individually before concatenating the results. The text also provides an equation for calculating the time consumption for the blockwise cross-entropy computation method, but does not explain the components of the equation in detail. This distributed training approach, inclusive of pipeline, data, and optimizer parallelism, is dubbed as Method 2 and aims to achieve high LLM training performance even on low bandwidth connections without exceeding GPU memory limits. The given text provides technical details about the performance of the YUAN 2.0 model and its training methods, as well as information on supervised fine-tuning and the creation of a Chinese tokenizer. It starts by discussing the time consumption for a distributed training method called YUAN 2.0 with LFA, providing a complex equation to calculate this metric. When tested, the model's performance on a GPU cluster was close to the predicted values with a low error rate of only 3.2%. Table 6 illustrates the predicted time performance of YUAN 2.0 across different AI chip configurations, ranging from 96 to 256 chips and varying peer-to-peer P2P bandwidths, 100 gigabytes per sec, 200 gigabytes per sec, and 400 gigabytes per sec. Method 2 consistently outperformed Method 1, showing minimal performance degradation when P2P bandwidth decreased. Unlike Method 1, which had a sharp drop in performance, for the supervised fine-tuning (SFT) phase, specific hyperparameters are used, including learning rate, sequence length, batch size, weight decay, and dropout rate. The Yuan 2.0 models are fine-tuned after pre-training, utilizing a truncated input approach during SFT to align the language model's behavior with human expectations. The fine-tuning process occurs over 4 epochs. Lastly, the text describes the process for creating a Chinese tokenizer using the sentence piece unigram approach on a substantial Chinese corpus from varied sources. The corpus was split into 135 files, with each one used to train an individual tokenizer with a vocabulary of 30,000. These tokenizers were then combined into a final version, using a weighted average to merge probability scores. The text discusses the development of a Chinese tokenizer, Yuan 2.0, which underwent a specific refinement process. The tokenizer started by assigning weights based on byte size to tokens from data files. After merging tokenizers, tokens with digits, letters, special non-keyboard signs, or more than 7 Chinese characters were removed. The remaining tokens were sorted by probability scores, with the top 50,000 kept. To avoid problems with unrecognized words, 9,000 individual Chinese characters and 30,000 uncommon words were added, resulting in a merged tokenizer vocabulary of 73,417. This tokenizer was then combined with other existing tokenizers to create the Yuan 2.0 tokenizer with a vocabulary of 134,953. In the results and analysis section, the performance of 3 versions of Yuan 2.0 of different sizes, 102B, 51B, and 2B parameters, is reported along with their training losses. The models were trained on a GPU cluster using the fill-in-the-middle (IMP) method. Training loss is shown for the 102B model, trained on 288 billion tokens. The code generation capabilities of Yuan 2.0 were assessed using the human eval benchmark, employing a greedy decoding strategy for zero-shot tasks. The model's performance, in comparison to others, is detailed in a table, and the approach to adapting English prompts to Chinese QA formats is mentioned, with GPT-4 being used for translation. In summary, the text outlines the creation of an extensive Chinese tokenizer and reports on the training methods and evaluation results of a series of increasingly complex Yuan 2.0 models, highlighting their code generation capabilities.